One of the more fulfilling aspects of being a computer scientist is interacting with end users, hearing their stories about the kinds of systems they want built, and then building those systems. So we've looked at how we declare and use account objects, but how did we design such an object in the first place? In terms of interacting with an end user, this often begins with what's called a user story. The user describes the object in terms of its properties and the functionality it offers. We respond to that story by defining instance variables, which we hide by declaring them private from the outside world, and methods which we make visible to the outside world to give our object the functionality the end user wants. Now in design, there are no right or wrong choices, but every solution you come up with usually has its own advantages and disadvantages. For the account object, a user might tell us that it has a need for a balance. We have to record the balance in everybody's account. This leads us to create an instance variable, and the phrase has a is code for needs an instance variable. In a user story, when you hear has a, you should be thinking, okay, I've got to think about an instance variable for this particular object to hold that property. It's almost always initialized in the constructor, but this depends on the user story and the nature of the instance variable. So if we say an account has an initial balance, when any account is instantiated, it has to have an initial balance, and we have to provision an account balance inside of it as an instance variable. So let's go through a bit of a user story and see how that leads to our object design. You're initially approached by a user who says, I need an account object. This leads you to create public class account, the definition of an account class. The user might go on to say the account has a balance. That means we must provision for the balance. What is the right choice of data type for the balance? Well, there's no right or wrong answer here. It might be an int, as we've used, or maybe you want to use a double to capture fractional dollars as cents. In any case, if we decide it's an int for now, we would then declare an instance variable, private int balance. Accounts are specified with an initial balance. The user tells us this. This leads us to create a constructor that accepts the information necessary for instantiating the account. We write the constructor to take in an integer, here we call it b, and then we assign the account balance, this dot balance, by initializing it to the value of b. Or perhaps you were not told that an account has an initial balance. If you were creating accounts in a bank, what would you make the initial balance if nobody told you what it should be? My guess is we would decide it should be 0, that no funds have been deposited yet. In that case, the constructor would take in no information, so it has void parameters, nothing is inside the parentheses, but it would assign the balance, this dot balance, the value of 0. It's possible that an object has both constructors because they have different signatures. So now we can create an account either with a pre-existing balance initially, or not, in which case its balance would be 0. We have a shorthand way of having one constructor refer to another. Here we see the code for initializing the balance to 0 is replaced by the phrase this, parenthesis 0, close parenthesis. What this means is to call another constructor that matches the signature of the parameters, namely the constructor shown above this one. If we create an account by saying new account and don't provide an initial balance, this constructor will run, but it delegates its activity to the other constructor, namely the one that does take in an integer. Now the user also tells us you should be able to find out the balance of an account. That seems like a reasonable thing to do. And based on that part of the story, we would create a public method called getBalance that returns or accesses the value of the instance variable by returning this dot balance. The user might go on to say, I want to be able to deposit funds into an account. Now we could think about doing this a couple of ways. We might say, we'll create a setter that would take in the new balance of the account and simply set the balance to that. So if I have $100 in my account, I could just change it to $1,000 without really thinking about depositing the money. That doesn't seem to match the user's story, and it also opens up our code such that the balance could just be changed, perhaps even taking money away. Instead, it's better to put in a specific method to accomplish what the user wanted. In this case, we'll call it deposit, and it takes in the amount of money to be deposited, and we compute the new balance by adding that funds to this dot balance. So here we see this dot balance plus equal f, the incoming parameter. That shorthand for this dot balance is equal to this dot balance plus f, and in this way we add the funds for the deposit into the balance ourselves rather than relying on something outside of our object to properly compute that result. If you look at this diagram, we see an account with two instance variables provisioned inside of it. So if the user had told us that we needed two pieces of information, we might provision them by adding private int x and y, and the small bubbles inside the larger diagram show the existence of these instance variables. As more instance variables are added, more bubbles are added to the diagram, so the doubles a, b, and c can also be accommodated. In terms of the interface to the outside world, the diagram also shows those interactions with the methods and their signatures that are supplied for the outside world to use. For the account object, we have getBalance to return the balance of the account and deposit to put in funds. Now, we didn't talk about this explicitly, but it's likely we would be able to withdraw money from an account. A user might say, I'd like to be able to withdraw money from an account, and they may want to specify how much money they wish to withdraw. If so, we would provision a method such as withdraw that might take in an integer c and deduct c from the balance of the specified account. You see here that this method returns Boolean. Why does it need to return a result? Well, you might not have thought of this, or the end user might not have thought of this, but eventually you're going to come to the conclusion that the account may not have sufficient funds to satisfy the withdraw method. So you would reach, perhaps in the second iteration of design, the need for this method to return whether it was successful or not. So this method might return true if sufficient funds are available, or false if they are not. Finally, we might want to be able to transfer money from one account to another. If a user tells you, I want to be able to transfer funds from this account to another, what information does such a method have to take in? It must take in the destination account that should receive the funds, that's the first parameter A shown here, and the amount of funds that should be transferred, and that's the second parameter. By providing this transfer method, we're able to transfer money from this account into account A. It's likely that the implementation would use the withdraw and deposit methods we've already constructed, we've already provided for this particular object. We might also decide that transfer, because it involves withdrawing money, might also return Boolean about whether it was successful or not, depending upon whether sufficient funds were available to do the transfer.